Yeah, it's a great idea to go through the literature and make sure things are recorded in the right way instead of just based on news media. So it's a long history about this estimate that I have been working with. The Li-Yau inequality and later extension actually went back to my understanding of understanding harmonic functions. So first of all, one of the main interests for geometry, as far as I'm concerned, is to understand the geometric structure of the manifolds. Starting from topology, we want to build some canonical structure over the topology of the manifold. So that could be canonical metrics, similar to Einstein metrics is one of the important metric that has been very important, both for physics and also for geometry. And an important Calabi conjecture was actually to construct Einstein metric among Kähler manifolds. So this has been very useful for algebraic geometry and string theory, and presumably it will be useful in number theory eventually. Just like in the case of the elliptic curve, where we have the metric, which is flat, but even for a flat metric, there are many ways to write it. Weierstrass P function and others has been very important, and they play an important role also in Riemann surfaces theory, in number theory, in many, also string theory. So I think it's very important to understand canonical metrics. And of course, the standard homogeneous metric, which are important prototype for us to construct metrics in general. In order to construct something that we don't know, we better to know something that we know already. We know the geometrization conjecture is one of the most spectacular problems in geometry and in mathematics in general, based on almost nothing except the topology of the free manifold. We want to construct some canonical structure over it. This was well known in many ways, but it was explicitly planned as a global strategy to understand free manifold by Bill Preston. So there are 8 types of geometry. Of course, the most important geometry is hyperbolic geometry in many ways. Anyway, to find canonical metric of manifold in many ways is to reduce to solve some elliptic type PDE, those that we are interested in, unless we go to general relativity, where the Einstein equation is hyperbolic, and then we have to look into hyperbolic metrics. But in any case, at least a large part of analysis that we have been dealing with are elliptic. And it's important because elliptic provides finite dimensionality, provides regularity, and all kinds of very important concepts that are important for geometry. Presumably, that's only because the limitation of our knowledge, but at least at this moment, we need to digest these large part of structures that we are dealing with. So, well, first of all, we want to know that how to decompose a manifold into many pieces, finite number of pieces, so that each piece emits some nice metric or nice structure. It could be a phi structure, it could be different kind of structure, and this has been generalized and been understood by many cases also, but it's not as fruitful as the metric version at this moment. So as I mentioned, the major conjecture starting by Thurston, geometrization conjecture, says that every compact orientable free manifold as a decomposition as with finite number of disjoint union, such that every component emits a locally homogeneous metric. As I said, the hyperbolic metric is one of the major ones. This, of course, including spherical pieces and all that. So the Ricci flow as a parabolic type PDE is an important tool to accomplish this decomposition. And this was expected long ago, but finally accomplished by Perelman. But I want to study one part of the estimate that was involved in the Ricci flow. So I want to mention some history here, as was asked to do so by you. So actually, in the early 1980s, Peter Li and I studied the heat equation and manifold and found an important inequality for the positive solutions of this equation. This method actually went back all the way to me in 1974 about doing gradient estimate for positive harmonic functions of manifolds, which I shall point out a little bit later. So this was useful for many purposes, and the work actually was done before 1986. I think maybe misprint here, 1983 or so. Anyway, it gave a very precise estimate of the heat kernel. And so when Hamilton started his first paper on Ricci flow, which he has initiated the flow, I think in the 1970s, late 70s, when I met him in Cornell. He's already interested in understand Ricci flow as a generalization of the Yu-Sampson approach to harmonic maps. So remember, actually, Hamilton worked on harmonic maps before the Ricci flow, and he did a nice, beautiful work for that. And Yu-Sampson's method of heat equation was a major tool at that point to study harmonic maps. And Hamilton wanted to do an analog for a diffusion equation in the space of metric. Actually, this is not just due to Hamilton, but many people want to think in that way too, including myself and Ricci. But we found that difficult to handle the equation, complicated and all that. It was a true tour de force that Hamilton was able to go ahead, actually understand the important cases first. So the first important case was done by him in early 1980s. I think he finished well in 1981. And for free manifolds with positive Ricci curvature, where he proved the Ricci flow exists for all time and it converges up to diffeomorphism equivalence to manifolds with constant curvature, positive curvature. So that was a spectacular work. And I invite him to give a talk in 1982 in the Institute for Advanced Study in Princeton. So he stayed in Princeton for 1 week, and we went through his argument closely in great detail. And I found it amazingly beautiful. And many of the results, actually, some of the arguments was truly creative by him. Some of them turns out to be actually non-trivial overlap with the work that I did on harmonic functions, the gradient estimate, the kind of argument that we use. So I proposed to him that he should use the Ricci flow to prove the Poincare conjecture or the geometrization conjecture at that time. So in fact, I have about 4 students immediately working on this problem of Ricci flow. Is including Cao Haidong, one of my first Chinese students, and Ben Zhao, and then C. Wang C comes later, but there was also Bundle who works in Ricci flow. But from the experience on harmonic maps, which a very important work was done by Sachs and Rudenberg. And in the case of Sachs-Rudenberg, it can be used to construct minimal surfaces. And this has been a very important tool to construct minimal surfaces in the general Riemann manifold. And we know already in there's bubbling phenomena. Although the function, the mapping is defined on a smooth sphere, then gradually the concentration of energy, and you need to bubble off a finite number of processes to construct a bubbling of spheres. And this has been very fundamental tool in geometric analysis in the 1970s. And when Sachs and Rudenberg did it in 1974, I think around, and I've used it for many other purposes. This including the proof of the Frankel conjecture that Xiu and I used, where we proved that the rational curve exists on an algebraic manifold with positive bisectional curvature, making use of Sachs-Rudenberg's solution to the harmonic sphere problem, and we proved that it's always holomorphic. So the bubbling phenomena exists already. And I suggest to Hamilton that an important question was to handle the bubbling phenomena, namely when the singularity occurs, concentration of energy, we need to know how to cut it off and decompose it in a suitable manner. And you have to prove finite number of bubbling so that we can handle the topology and all that. So in order to understand the singularity in bubbling, one needs good control of the phenomena, and this was analysis of the Ricci flow. One needs estimate to control what can happen. So this was a major task right after his discovery of the important theorem that every free manifold reports a Ricci curvature converge according to Ricci flow to the good round manifold with constant positive curvature. Well, in order to understand this problem, Hamilton tried to do an analog with mean curvature flow, and he worked with Mark Clayson about curve shortening flow and all that. And then later, Hodgkin come in to understand the mean curvature flow, which are very inspiring to the Ricci flow. And so Hamilton still needs to know exactly how to handle the singularity. Well, in the late 1980s, in 1988, I moved to San Diego, and first thing I did was to offer Hamilton a job in San Diego. His office was right next door to me, to my office in San Diego. Well, so we discussed quite extensively about the estimate. And I point out the heat kernel estimate that I did repeatedly on scalar functions on manifolds with positive Ricci curvature. The reason I mention this inequality is because this is the only estimate that is very precise, sharp. The constants are the best constants. So in the case of Euclidean space, the Li-Yau estimate for the heat kernel becomes the standard heat kernel. So it was very sharp, and I talked with Hamilton. We think in order to understand the geometry behind the Ricci flow, one needs a very, very precise estimate. Otherwise, things got lost. So he started to talk with me about how to generalize this estimate. So in 1993, he discovered a rather spectacular non-trivial matrix version. By 2002, as we well know, that Perelman actually wrote the paper about the Ricci flow, how it can be used to solve the Poincare conjecture. There's actually, he also used the Li-Yau estimate to the conjugate heat equation to obtain the non-collapsing estimate for the Ricci flow. First of all, for the function, and then for Ricci flow. And he used Hamilton's version, which I will talk about it later, to get the formulation, to understand the formulation of singularity. This actually is a very important argument, ingredients for the surgery of Ricci flow, and therefore the proof of the Poincare and the generalization conjectures. So let me start out from more detail. That was the introduction. So this was done actually in 1973, 74. It was published in 1975. So let U be a positive harmonic function on a manifold with Ricci curvature, which is a lower bound, which is the lower bound is minus n-1 k, where k is a constant. I was mostly interested when k equals 0. That was a important question for me because I was trying to prove the Franco conjecture. And this was a starting estimate that I did. So in 1974, I finished the argument for proving a Liouville theorem for harmonic functions on a manifold with non-negative Ricci curvature, which says that any positive harmonic function must be constant. So I introduced the following function, phi equal to gradient u divided by u, where u is a positive function. So some positivity is needed so that I can divide it by u. And then I proved that the Laplacian of this function satisfies this inequality. This inequality, the first term is important. Originally, it was a Hessian square, but I managed it so that it becomes bigger than equal to this element, 1 over n-1 grad u grad of that square. This is a very important simple trick, and also Hamilton also used a similar thing for his work on positive Ricci curvature on free manifolds. So it's important because I squeezed out some non-trivial useful quantity, which depend on dimension 1 over n-1. So the final result after understand this inequality, I applied the maximum principle. I proved the following inequality, namely gradient u over u is less than equal to constant. In a ball radius r, the constant times 1 plus r squared root k divided by r. So the very important statement here is that the estimate here depending only on the lower bound of the Ricci curvature. No other things were involved. This is very good because when we work on manifold with non-negative Ricci curvature, we do not know much geometry about it at the beginning. And the estimate here tells you that the right-hand side only depends on lower bound Ricci curvature. So if k equals 0, when the Ricci curvature is non-negative, it is only 1 over r. If r go to infinity, the right-hand side go to 0. This would mean the right-hand side is identical to 0, and gradient u over u would be equal to 0. And that will mean u is a constant. That's why this inequality implies the Liouville theorem, which says that positive harmonic function must be constant. So this gives you a quantitative version of the Liouville theorem, that for a positive harmonic function, we can control gradient u over u. Gradient u over u is actually just gradient log u, as you can say. And this controls the oscillation of the log U, how they behave. So as I said, it's one of my goals. We prove that non-negative Ricci curvature does not exist, non-constant harmonic function. This also is implies the Hanna inequality for positive harmonic function, which we learn in complex analysis. And given any 2 points, we can join these 2 points in a ball radius R/2 by geodesic, and then we integrate around the geodesic. It says that UX1 is less than UX2 up to a constant, which depends only on the lower bound Ricci curvature. So this is a inequality comparing functions at different points as long as they are positive. So they cannot go too fast to 0 or too fast to infinity because they balance out against each other. So this inequality actually is a sharp version of the maximal principle or minimal principle. So if U equal 0 at one point, then U is 0 everywhere if it's non-negative harmonic function, as you see from this inequality. So this is a good control on oscillation of positive, non-negative harmonic functions. Well, soon afterwards, Peter Li and I worked on this problem. We generalized this estimate from harmonic functions to eigenfunctions. So there's a similar operator, Laplace of the function equal to minus a constant times the function. So from harmonic functions to eigen functions is rather natural. The understanding of eigenfunctions, of course, dates back to early days, maybe even earlier than Hermann. But Hermann was really the very first one to make eigenfunctions relate to geometry in an extensive way. He solved a problem of Hilbert. Actually, Hilbert learned this problem from Lorentz on the asymptotic behavior of eigenvalues of a Laplacian in relation to the volume of the manifold. In the 1970s, part of Peter Li's thesis in 1978, where he makes some assumptions, and later we generalize it together, extend the gradient estimate for eigenfunctions to solve several interesting problems where we can estimate eigenvalues of a manifold in terms of the diameter and the lower bound of the Ricci curvature. It follows a similar estimate, the gradient estimate that I just mentioned earlier that I did for harmonic functions. And also I used the same method with Peter Li to give a version of polar conjecture, which claims a very precise estimate of the eigenvalue behavior. And we proved the average version of the polar conjecture, which proposed to give a sharp lower bound of the Dirichlet problem eigenvalues in terms of volume. This is a beautiful conjecture which is still not completely known. But based on this estimate, we proved the average version. And then S.Y. Chang and I start to use this same idea, the circle idea, to solve several problems in geometry. A very rather important problem at that time was to prove the maximal slice in Minkowski space. So there's a well-known Bernstein problem for minimal graphs in Euclidean space, which can be written in the following form: 1 plus gradient U squared Laplacian U minus the Hessian of U times gradient U times gradient U squared. Well, in 1914, Bernstein proved that every entire solution of this equation is linear for n equal 2. The method was based on conformal geometry and complex analysis. This has been a very important question in minimal surface theory in geometry. And this is related to regularity of area minimizing hypersurface in general manifold, actually, although it looks simple. This problem was settled finally by many important geometers and people working in analysis. The Federer, Fleming, Di Giorgi, Armagon, Simons, Pompiali, Di Giorgi, Giusti. So the Bernstein problem was actually basically solved by the last few people. And it turns out the answer is that it has only linear entire solutions for n less than or equal to 7, and they are non-trivial entire solutions for n bigger than 7. We are interested in this problem because of regularity of the problem for divergence-free equations in general. And turns out if we look at same problem instead of in Euclidean space, we look at it in Minkowski space, then we change the sign from minus to plus. So all the signs in this equation from plus, we change to minus, minus to plus. It becomes this equation. This is the same kind of problem, except it's a maximal space-like hypersurface in Minkowski term with coordinate like that. And then one asks the same kind of question. Calabi proved that this equation has only linear entire solutions for n less than or equal to 4. So it was a curiosity to know whether similar phenomena of Bernstein problem appears. That means it may be true up to some dimension, like n less than or equal to 7. Well, it turns out we proved that it's not the case. In 1976, Chen and I make use of a similar idea that I used to treat harmonic functions by looking at this following function, where A is a ball radius A, and then R is a distance function that we construct in the spacetime. And then we look at the second fundamental form. And we give a good, interesting estimate for this and prove that it is actually true in general. That means there's all the entire solutions for the maximal space-time hypersurface are linear. So this is a very important application of the idea that I brought out for the harmonic functions. And then there's another important question, is also a Bernstein problem. So affine geometry, we look at the motion pair equation and take determinant equal to 1. When U is convex, that is needed because we want to make sure it's elliptic. And this is actually has a beautiful geometric meaning, which is called affine sphere. Sometimes it's called improper affine sphere. There's another affine sphere, hyperbolic affine sphere. The equation is determinant of the Hessian equal to -1 over u to the power n plus 2. These are called hyperbolic, and they are very interesting and important objects in affine geometry. So for this equation, it was similar, namely for n equal to 2. It was proved by a German mathematician, Jürgens, that this equation has only linear quadratic polynomial solution. Because if U is quadratic, the Hessian is constant, then clearly you can make it to be determinant equal to 1. So one asks the converse, whether the entire solution of this equation is always quadratic polynomial or not. So this was also studied by Calabi, and he wants to make sure something called affine metric related to this is complete, and then he wants to prove that if it's complete, then the affine sphere is elliptic or parabolic. So the equation, the Bernstein problem, namely to prove that this equation has only quadratic polynomial solution, was reduced actually to prove something called affine metric is complete. Complete as a Riemannian metric. Calabi proved this one is true when it is defined over affine sphere with dimension less than or equal to 5. And he proved the alpha matrix is complete. So whether it's true for arbitrary dimension was left open. And in 1986, so actually 1986 was the time where this paper was published. This paper was done in 1974, and we published it after 10 years. The reason we delayed the publication is that Nirenberg said that he could do the same thing by a different method. We were thinking to work with him together to publish a paper. It turns out he never write up his paper, and he urged us to publish it independently. So we published the paper in 1986. We proved that it is the alpha matrix is always complete. So all these are based on very sharp estimate that we found out in terms of the harmonic function, the argument that we use. Well, then in around 1986, Peter Li and I extend this gradient estimate from Laplace equation to a heat equation. These dates are all actually somewhat mistaken. I think it was earlier than that. Anyway, we look at the following equation. So naturally, we look up the heat equation that could appear, which is d over dt minus Laplacian acting on u equals 0. So from Laplace equation to heat equation. But we want to add a potential Qx there, because naturally, when you write down this equation, you think about dynamics, and there could be an interesting question to add the potential function to look at how particle diffuse around. And so we want to understand this estimate, this U. Actually, even for Euclidean space or domain in Euclidean space, there's a large amount of work on this kind of problem. The argument based on super inequality, the argument based on many different approach, but they have a good estimate, but they're not sharp in the sense that you can find estimate that actually becomes an equality in important cases. So we were looking for such a estimate, which will reflect as a sharp estimate. We need sharp estimate because that will give you a precise understanding of the geometry behind it. So we introduced this following expression. So gradient u squared over u squared, this part is similar to the elliptic part. And we look at this ut over u and n over 2t because of parabolic situation. And it turns out this guy is a very important quantity. After a lot of attempt and struggle, we proved the following inequality. Namely, suppose the potential has some control, gradient of Q. Q is a potential that appears. So the potential appears in this equation. So heat equation plus the potential. So we need some control on the potential. Gradient is control in terms of some function, which is kind of linear in linear growth, and upper bound. And then the Laplacian has an upper bound of Q. The theta is a constant as here. You can generalize it, but we are pretty happy with what we see here. Then we prove this inequality in the last line. So it's plus Q plus all this. This turns out to be very precise estimate. This holds true among manifolds with non-negative Ricci curvature, and is achieved by the heat kernel of Euclidean space. So in other words, this expression is identical to 0 in the case of non-negative Ricci curvature. Is non-positive for all positive solutions of the heat equation, and is identical zero in the case of heat kernel on Rn. This is actually a very precise estimate and is important for the development that Hamilton and Perelman later used to use. This we want to adapt to the Ricci flow and the conjugate heat equation. So for the Ricci flow, the generalization was done by Hamilton, and the conjugate heat equation was used by Perelman. Now, if I use this inequality that I wrote down here, the bottom of this page, is an inequality. I can integrate it along a path. When I integrate along a path, I got the following inequality. So the U, the solution for the heat equation, at one point in space and time, x comma t1, can be compared with U at the other point, y and t2. So when the heat diffused in a manifold, we can compare the value of them at different points. And the discrepancy is given by T2 over T1 to the power n over 2, and then exponential of the right-hand side. If we don't have the potential, C could be set equal to 0. So here we put some C here because of the potential. But if we don't have potential, then C could be set to be equal to 0. And then it will be exponential of log x comma y t2 minus t1. This is a very important quantity that appears later. This actually can come from Hamiltonian mechanics, and it is equal to log x comma y t2 minus t1 is defined by this minimizing procedure, where gamma is any function joining y to x. So integrate from 0 to 1 of the energy of the gamma, and then plus T2 minus T1 is the integrate of the potential energy. So this is a very important quantity in Hamiltonian mechanics. And the beautiful thing is that we prove that the heat kernel oscillation is measured by this function precisely. And as I said, this actually becomes equality in the case of Euclidean space itself. And this is very important because this quantity appears as an important geometric quantity later. Okay, this function we call the low distance between any 2 points in space-time. This was already introduced by Peter Li and I, and appear in several other places. So in the case of Q equals 0, which is the most important cases, but you can generalize it naturally. But in that case, we derive, we look at this law and look at its variational problem, d law over dt, gradient law square, etc. And we prove that last inequality, the Laplacian of law is less than or equal n over 2t plus n theta over 2. The theta appears in relation to the Laplacian of Q. It's the upper bound of Laplacian of Q. That's how it comes out. So this is a beautiful quantity law satisfies d law over dt equal this and gradient law equal that. And you can now see that it solves a interesting combination, namely the Schrödinger equation d over dt minus Laplacian by minus q apply on here is less than or equal to 0. If you remember, this quantity appears in the Li-Yau estimate. So it appears in here and here. So we prove that this quantity law satisfies this very nice inequality. So then, by looking at this inequality, we can derive several important consequences, which appear in my paper with Peter Li. If we define the volume vector volume by integrate the right hand side, integrate 4 pi 2 t minus n over 2 exponential of that. This is a beautiful volume, with importantly because of the inequality that we did is monotonically non-increasing in time t. And the fundamental solution, which we can derive from the Schrödinger equation, the operator d over dt minus alpha minus q, satisfy this very important inequality. That x is the fundamental solution. X, y, and t is bigger than the right-hand side. And this, as I said, is sharp inequality. The very importantly is this law plays a very important role for this heat kernel estimate. This estimate, as I said, cannot be obtained by other methods, which they use super inequality and all that. And this is a very good and important estimate, minus low xyt. So, well, we can check easily the low xyt is actually asymptotic to d squared xy divided by 4t when t go to 0. And this is very important because this reflects exactly how the heat kernel looks like for Euclidean space, which is given by d squared over 4t. Now, remember, it's extremely important to recover this constant 4. In most estimates that I know, 4 is not there. They have to give by a smaller number to make the estimate work. But we need this 4 in order to compare with Euclidean space. We know if we look at this, we can tell the Vt when t is small, the volume that we just defined, this volume that we define here, the vector volume, actually is asymptotic volume of ball radius square root t divided by t to the power n over 2. So if we fix for fixed capital T, Vt can therefore be estimated is lower bound by constant kappa by taking limit, and then by the monotonicity of the volume. We know therefore volume of Bry divided by r to the power n is bigger than or equal to kappa, always by monotonicity for all r less than or equal to square root of t bigger than 0. Sometimes later on, it was called by Perelman and others to be non-collapsing around y. So therefore, it's non-collapsing around y up to all scales less than or equal to square root of t. So this is a parabolic equation, r square root of t in the same scale. That's why we have that. The space we define on the space on space-time m cross this interval. So we may consider as in this space with a general evolving metric Gij denoted by this equation. D over dt Gij xt equal to minus 2 mu ij xt. Well, it's easy to know that in terms of volume, using this flow, d over dt of the volume is like minus trace. It's a pretty standard thing. So determinant becomes trace, and you understand the monotonicity of the corresponding Li-Yau volume for the evolving metric. One should consider this equation to cancel the variation from the volume form. Well, the same argument will give a corresponding Li-Yau inequality, low distance, and the monotonicity of the Li-Yau volume for the evolving metric Gij xt. So we can do the same thing with background changing at Gij t, and everything is the same as before. So at the beginning, when we first did it, we assume the background metric is fixed. But if the background metric is moving according to time by this simple statement, mu ij, well, in the case of Ricci flow, mu ij is simply the Ricci curvature. We know how to move it, and we can do the same thing as the vector volume that I mentioned, the monotonicity, all of them are actually there by simply changing it in that way. Well, in a Ricci flow, one hopes to get a non-collapsing estimate of the evolving metric at the time t equal to capital T in terms of the initial metric. So we want to look at the global behavior of the metric at the last time that we got into trouble at t equal to capital T. In terms of the initial metric, where we know everything is good, the initial metric. So we therefore, one should consider the bedrock heat equation. This was what Perelman looked at. So look at the bedrock heat equation, and the potential is naturally scalar curvature because the natural potential in gravity is a scalar curvature, as was introduced by Hubert. Hubert action says that the potential should be scalar curvature. So the Q that we mentioned before is now changed by the scalar curvature. And tau is T minus capital T minus small t, because we're looking at things bedrockly. This sometimes can be called a conjugate heat equation because if you look at the conjugates of the, just like an operator has a conjugate operator, then you get a conjugate heat equation. And this equation is what Perelman studied. Then you can define the similar low distance and the volume that I mentioned in my paper with Peter Li. And this was called reduced distance and reduced volume by Perelman. And this is corresponding Li-Yau estimate is important estimate for Perelman's non-collapsing result. Okay. So far, we have been dealing with the estimate, the Li-Yau estimate for scalar function. But now, as we know, the major thing for Richard Hamilton was a tensor equation, d over dt of Gij equal to minus 2 times Rij, which is a parabolic evolution equation on the space of metrics. So in order to understand generalize the Li-Yau estimate, we need to go to a matrix version of this whole thing. So if we know, look at this equation, we can do a simple calculation, namely look at the scalar curvature of the Gij. Then you look at the heat equation, scalar curvature, then it is equal to Rij squared. So this is good because it says that scalar curvature tends to move up. It is originally positive, then it is keep on positive. So let us look at the two-dimensional case, and scalar curvature satisfies this interesting inequality. So d over dt minus Laplace minus r, because r is a potential. That's the equation that Li and Yau consider, but now replacing q by the scalar curvature. Well, compared with the original inequality that Li-Yau used, then we want to study this inequality. Gradient r squared divided by r squared minus rt over r minus 1 over t. So we're interested in this inequality. And this exactly this inequality which Hamilton proved for the Ricci flow on the surfaces. And this is very interesting and important hint to know what to do for 3 dimension. Well, for high dimension, the curvature operator is a matrix, is a tensor, and satisfies a complicated evolution equation. You want to look at the whole curvature operator. Well, the important thing is to find the correct expression that we can estimate. So you see, we have this expression, d over dt of r minus gradient r squared over r plus r over t. This is an important quantity. So let me show it to you. The way that I did repeatedly, we use this quantity. Sorry. we use this quantity. Gradient u squared over u squared minus ut over u minus n over 2t. U can be looked at, if you look at it in terms of log, this becomes simpler. That's how we use this one. But this, we need a different way of looking at this expression. The best way to look at this expression is actually multiply the whole thing by u squared. After you multiply whole thing by u squared, it becomes a quadratic expression. So multiply this whole thing by u squared. The first term is gradient u squared, and then minus u times ut, and then minus n over 2t times u squared. So every quantity becomes quadratic. Well, we want quadratic because multilinear form or bilinear form, then we can adapt it to curvature. So that's how it comes out. So I talked with Hamilton pretty extensively what is the right quantity to replace the quantity that Li and Yau use. So we've figured out that it's better to be quadratic. And this was done by Hamilton in a very non-trivial manner, very creative manner. It took him about 3 years to accomplish this inequality. Although in a funny way, for doing these kind of things, you may think about it for a few years, but after you know the right quantity, you can probably prove in a matter of 1 hour, 2 hours. So what one needs to do is to prove that the inequality you want to prove is true for some kind of soliton, which is the extremal behavior of the metric situation. So you want the inequality to hold for all metric that satisfy the Ricci flow. You want to go to an extreme case of the inequality. So one want to test it out for an expanding solution, and this was finally achieved by Hamilton, as I said. He proved that if the initial metric has non-negative curvature operator, then this inequality holds for any vector v that makes the inequality holds. This is a very non-trivial statement. It comes from a matrix, a tensor inequality. So this one is obtained by taking a trace of a tensor inequality for curvature operator. It's amazing work, I think. And somehow, when people talk about Ricci flow, very few people talk about this important estimate, which took Hamilton quite a few years to achieve. Well, the important thing is for the scalar curvature, therefore, it satisfies this inequality. You can compare the scalar curvature at a point in spacetime with the scalar curvature at another point, and the discrepancy is measured by this quantity T2 over T1, d squared over 2T2 minus T1. So we can define the distance similar to what I did with Peter Lee. So this is an important fact. And then out of those inequality, one also conclude that so-called type 2 and type 3 singularity model with non-negative curvature operator must be a steady Ricci soliton. In the case of type 3, is expanding Ricci soliton. So the Ricci flow provides a way to deform arbitrary metric, but in this argument, Hamilton needs the metric to be a non-negative curvature operator. Well, one needs some positivity for the whole theory that Li and Yau use, because we make assumption that we only deal with the positive solution of the heat equation. So we need to have some initial assumption, namely positivity. And this was used in Hamilton, assuming some kind of positivity curvature. Now, once you say that this is important, but one would like to relax it somewhat. because in the Li-Yau estimate, we can actually allow the Ricci curvature to be negative also, although you didn't get a sharp estimate. Before Perelman proved the Poincaré conjecture, Hamilton and I was trying to generalize this estimate to more than just non-negative curvature operator. This, as far as I know, is still not known. It was a good generalization. Anyway, this curvature operator non-negativity is good enough for applications. The reason is there was an important work due to Hamilton and Ivy where they proved a curvature pinching estimate in the Ricci flow. The pinching estimate roughly says that if a solution to a Ricci flow in a free manifold becomes singular, the curvature goes to infinity as time approaches, then the most negative central curvature will be small compared to the most positive central curvature part. So therefore, around the singularity, the curvature operator will become more non-negative. And therefore, Hamilton's Li-Yau inequality can be applied in understand the singularity, the formation of singularities. So with this preparation by Hamilton's important work on the estimate on the Ricci flow, the Ricci curvature and all that, we can now understand formation of singularity by rescaling the metric near the singularity, which is a rather standard thing to do. It appears already in Sachs rule, but we want to rescale the things. Well, one needs to control the bounds on the curvature, and on the one hand, one needs to control the lower bounds of the injective radius. So we rescale the solution so that the rescale curvature becomes uniformly bound on compass sets and leave the injective radius of the rescale solution to be estimated. So that's pretty standard way of one do that. Well, turns out I have already studied some kind of injective estimate with Chen and S.Y. Chen and Peter Li, say in the early 1980s. This was published in American Journal of Mathematics. So the estimate says that if we have geodesic ball in an n-dimensional compact manifold, so the curvature has some pinch like this, then there's an estimate of the injective radius. The published version is slightly weaker than this, but it's basically the same as this. This was an important estimate because we can give some understanding the low bound of injective radius in terms of volume. So it relates injective radius bound to some lower volume bound, provide one localize the relevant geometric quantities appropriately. The lower volume estimate was achieved by Perelman in 2002 for the Ricci flow. Indeed, Perelman's non-correlation result is actually a direct consequence of the monotonicity of the volume for the conjugate heat equation, which was studied by him in the first part of his paper. The study of the conjugate heat equation and the volume that we devise from the heat equation. So Perelman studied this equation by looking at a non-corrupting estimate. So there's this flow that we're looking at, bedrock heat equation, tau equals T minus small t. And we look at this quantity, the expression which was devised by Peter Li and myself. Namely, we look at quantity where F is defined by the following quantity. When U is a solution, we look at U, look at F defined by this. This F is very much similar to log U as appear in my estimate repeatedly. So the Li-Yau expression turns out to be this one. And then if we set V equal this, then the direct computation gives the following equality, which is very similar to the forward heat equation. And then we integrate this quantity, the V, over the manifold is similar to the volume that we have there. And Perelman called this one to be W entropy. And the above equation becomes the monotonicity of the W entropy, which was also appear in the Li-Yau theory about monotonicity, which I mentioned earlier. So, as I said, U is fundamental solution. We define F by the quantity that I mentioned before. Then you get this inequality that was explicitly spelled out by Perelman for the Li-Yau type inequality in the conjugate heat equation. Then we do exactly what Peter Lee and I do. Once you know this quantity, we integrate along the paths in space-time. And by naturally integrate in a similar way, we get the following path inequality. And namely, if we define a path in this way, this is a rescale path similar to what we have in the case of heat equation, except because in bedrock heat equation, we do it differently. And this is a similar type of path that was introduced in space-time. Then one can prove that FQ tau bar is less than equal to this length function. And one can then estimate a lower bound to the fundamental solution for the conjugate heat equation. Namely, the lower bound is obtained in the last inequality. So this is similar to the heat kernel estimate for the forward for the original heat equation, where we have a lower bound in terms of low distance. Now it's in terms of the L distance. Now, as I mentioned before, we also have the reduced volume, the volume that we associate to it. Once we define a replacement of the low distance by Perelman, replace the low distance by this L distance, then we can look at the first and second variation formula according similar to what I did repeatedly. We found dl over d tau bar and gradient L squared and Laplace L all satisfy this inequality, which is an exact analog of what we did in the case of heat equation. And then we found that there's a K, which is obtained by this, which is similar to the quantity arise from the potential that we had there before. Then the combination gives this estimate, d over d tau bar minus Laplace plus r, acting on this quantity is less than or equal to 0. So this is exactly analog of what we did before, where L is replaced by rho. So the corresponding Li-Yau volume becomes a reduced volume of Perelman by just integrate this whole thing. And then in that way, it's monotonic, non-increasing in tau bar. So a direct consequence of this monotonicity of the reduced volume is the following non-corresponding result for the Ricci flow due to Perelman. Is that there exists a constant kappa depending only on capital T and the initial metric, so that if R0 is less than square root of T and the curvature is less than or equal to R0 to minus 2, this is similar to the potential part we need to make assumption on. Then we put the volume is bigger than or equal to kappa R0 to the power n. So this is a non-corresponding result of Perelman, which is important for the later geometric argument he used. It turns out one can extend this local non-corresponding result to weak solutions of Ricci flow with surgery, sometimes called surgically modified solutions. This is necessary in the proof of Poincaré and geometrization conjecture due to Perelman. In fact, what one do is that for the reduced distance, which was introduced there, one can define the associated exponential map and the associated Jacobian. So everything is similar. Once you have the distance function, we know how they look like in a small when tau equals 0. And we look at the L geodesic starting at P and look at its Jacobian along the path gamma. By the standard combination, which we know in Riemann geometry, you know how to compute exponential map. You know, compute the Jacobian or the exponential map. It is satisfied equation. The equation is d over d tau log of the Jacobian is equal to Laplacian L plus R. So one need to calculate it, but it's straightforward. The combination with the first Emeritus formula of L implies the following inequality observed by Perelman, namely this whole thing over d over d tau is less than or equal to 0. So this becomes a local version of the monotonicity of the reduced volume. By integrating the above inequality over a zeta of the tangent space of P, one will obtain a volume comparison theorem over the zeta. So this localizes the thing in a very nice, beautiful manner. And using this, one can do surgery. So one obtains a non-correlative result over the zeta, and one can do surgery over there. So the basic idea of Perelman can be briefly described as here. You start from an initial Riemann metric and then study the behavior of the solution to the Ricci flow. If the Ricci flow develops singularities, then one tries to find out the structure of singularity so that one can perform surgery by cutting off the singularities and then continue the Ricci flow after the surgery. Repeating the process of performing surgery and continue the Ricci flow again and again, then we hope to get to the best situation. But of course, it is extremely important that we know there's only finite number of surgery needed. Otherwise, the whole problem will be out of control. So we need to know that over finite time interval, there are only finite number of surgery. Well, if the long-term behavior of the solution of Ricci flow surgery is well understood, then one would recognize the topological structure of the initial free manifold. So after we know the Ricci flow after surgery, and if it needs only finite number of them, then we know the end result, and then going backward, we understand the topology of the original manifold. And so we need to use the estimate, the inequality that I mentioned to understand the structure of singularity and controlling the surgeries. This is a very spectacularly important work by Perelman. So the structure of singularity of Ricci flow on a free manifold, one wants to dilate the solution around the singularity so that the rescale sequence of solutions having uniformly bound curvature. This kind of argument was already started from minimal surface theory, where one always understands singularity by rescale around the singularity. And then one try to use the non-collapsing result to make sure that the convergence is good. One takes a limit of the rescale sequence. This will give a structure of the solution around the singularity. Well, at this here, by combining the Hamilton IV curvature pinching, we have that the limit is a solution of Ricci flow defined at least in the interval from -infinity to 0, and is a non-collapsing and with non-negative sectional curvature. This kind of solution would be called a Anson non-collapsing solution of the Ricci flow. I think it's called by Hamilton. Well, by Hamilton's inequality, one can prove the following universal quantitative control to all Anson non-collapsing solutions, which says that there exists a positive constant eta and a positive function with the following properties. Suppose it is a Anson non-collapsing solution, then the scalar curvature satisfies this estimate, which we can used to control the singularity. So the ratio between the scalar curvature is controlled in a suitable manner. The gradient grows at most like r to the power 3/2, etc. So this is a very important elliptic type estimate that was used by Perelman. If the ancient non-correlating solution is compact, using this estimate, elliptic type estimate, one can prove the free manifold must be the round sphere, and it is the theorem due to Hamilton in 1983. These are important arguments that dates back to long ago, up to. On the other hand, if the ancient non-collapsible solution is non-compact, then either the free manifold is an evolving round cylinder, or it is diffeomorphic to R3, splitting off a line at infinity and asymptotic to round cylinder at infinity. This is actually very similar to the Bernstein problem, where people used to do minimal surface to split out a line there. But one need to conclude the cylinder is round. By doing this, one has to use the uniqueness to the solution of Ricci flow on complete non-compact manifold, which was settled by Perelman for the special rotational symmetric space, and settled by Chen and Zhu for general case. This tells us that for any singularity of a solution to a three-dimensional Ricci flow, there's a canonical neighborhood around the singularity, which is very close to either a round neck or a cap with round color. So this is very important structure theorem about that. So then with this, Perelman is able to study Ricci flow with surgery. The concept of Ricci flow surgery was introduced by Hamilton, actually. So given a three-dimensional manifold with arbitrary Riemannian metric, one evolves the metric by the Ricci flow on a maximal time interval. Then the solution starts to develop singularity as t approaches capital T. Otherwise, we can just keep on moving. The singularity now has a canonical neighborhood, which is very close to either a closed neck or a cap with round color. One can cut off each canonical neighborhood along the boundary color of this neck or the cap to get free manifold with a finite number of connected components, omega j, and those with boundary. One can then glue back free balls along the boundary to get a closed free manifold. So this is a surgery argument. One try to remove something bad and then glue in with something that we know. Then the initial free manifold will then diffeomorphic to the connect sum of this omega j bar with a finite number of copies of S2 cos S1 or RP free. That was because we have all this cap and cylinder and all that. So this will give you a good understanding of the diffeomorphism class of the initial free manifold. Is a connect sum of these fellows and all that. Well, one wants to understand this omega j bar, and then we apply Ricci flow again. Then the solution also develops singularity. We perform the surgery again and again. Well, this kind of procedure, we need to stop sometime. We have to prove that. And we can do it with solution to Ricci flow also, we can call it. So sometimes it's called Ricci flow surgery. And to get the topological information, as we said, we have to prove that there are most a finite number of surgery at each finite time interval, and with a well understood long-term behavior. Well, in 1999, Hamilton obtained the long-term behavior for non-singular solution to a Ricci flow on free manifold. His argument can be modified to obtain the well-understood long-term behavior to these surgically modified solutions. How to prevent the accumulation of surgery time is the most important issue in the proof of the Poincaré conjecture, and of course the German-Tricidal conjecture also. The elliptic type estimate that we mentioned there, based on Hamilton's work, proved the key estimate. provide a key estimate to control the surgery procedure. Well, by the universal and quantitative estimates, one can find uniform size and curvature to recognize canonical neighborhoods. One can then cut down the solution so that its curvature never exceed such a desired uniform size, and hence each surgery will drop at least a finite amount of volume. By doing that, because the total volume is fixed, you cannot keep on losing volume with a fixed amount. This will prove that there are only finite number of surgery you need. So this is a very important way of doing things. Well, finally, we should remark the Ricci flow with surgery was first proposed, as I mentioned, by Hamilton in 1997. Although he has not been very successful to prove the accumulation of surgery would not be possible at that time, he established a lot of fundamental works for the geometric surgery by studying a similar case for four manifolds, where he treated positive isotropic curvature successfully. The work on four manifolds with positive isotropic curvature was a beautiful work by itself. Well, in 203, Perelman sketched a delicate and complicated argument to overcome the accumulation difficulty. And this complete write-up was written up in the paper by Carl and Zhu. And in the case, as I mentioned, four manifold with positive isotropic curvature is an independent, beautiful work on understanding four manifold with positive isotropic curvature. There's results due to several people about how it looks like, but only phlegmatically. And the final classification was due to Ricci flow, due to three authors, Chen, Tan, and Zhu. They extend the surgery argument to four dimensions to obtain this complete classification for manifolds with positive isotropic curvature. So this whole thing is a beautiful history in mathematics, a beautiful, important application of geometric analysis to topology. So I'll stop here. Thank you.
Professor Yau, thank you very much. If anyone has any questions, please ask or please put them in the chat. I'm going to start. So I wanted to ask if you could elaborate a little more on the history of what you were doing with Hamilton before the backwards heat equation, because Perelman introduced the backwards heat equation, and in his section 7 and section 9 of his paper, he basically, he goes through the first variation, the second variation, and all of these things that were already done in your paper with Peter Lee. So it seems a lot of the technology was already there, and I was wondering if you could sort of elaborate on that, what you guys were thinking before he introduced the backwards heat equation and in the context of non-negative curvature.
Well, Hamilton and I worked on this problem pretty extensively, but we were maybe looking at maybe going the wrong way, did we? But not completely wrong. We tried the hard way. We tried to relax the condition of non-negative central curvature or the curvature operator for the Hanna inequality or for the Hamilton inequality. That encountered some difficulty. We did many interesting inequalities, but not quite the result that we want for the surgery. But we are modeling the whole thing according to this talk I talked about. Many of our works were discussed extensively by Hamilton and myself, but also, of course, we should mention there are important works due to Xi, my former student, who died, unfortunately. And Xi has made a lot of contribution to the basic estimates too.
Okay, thank you.
Yeah. So as I said, by 1996 or 97, we kind of expect the Poincaré conjecture could be proved in this by Ricci flow. We were very excited about it. And we, in fact, tried to build a center in Hawaii because Hamilton likes Hawaii. We have actually called about 20 people together to work on the problem to finish it off. And we applied a center from NSF. We almost got a center to be built in Hawaii. University of Hawaii did not provide the space. And the center finally went to Ohio to study mathematical biology. So I regret that we didn't have the funding to group several people together.
I see. We have a question. Go ahead.
Thank you, Dr. Yao, for fascinating presentation. I was going to ask that, given the wide-ranging impact of Li-Yau inequalities, I was just curious, what has been most surprising or unexpected, perhaps, application of these inequalities in your experience? Were there any results that weren't anticipated?
Well, yes, surprised me somewhat, but on the other hand, it's probably not so surprising. As I said, the Li-Yau inequality actually was motivated by gradient estimate. And I know it's pretty powerful in the elliptic equations. So I think putting the heat would, the time would be very good. And in fact, this estimate, I was trying to understand some questions in quantum tunneling, actually, in relating to the Hamiltonian mechanics, how this comes up in the WKB method, so to speak. The Li-Yau estimate, actually, one can say that one can use it to prove the WKB method in one direction. WKB method is a way to using geometry to approximate particle solution and all that. And one need to two-side estimate, but it enable us to give one-side estimate is very precise. If you know the Polier conjecture, which I mentioned in the earlier of this talk, the Polier conjecture tells you the Y estimate, Hamilton Y estimate is true. Hamilton Y estimate tells you that there's a asymptotic behavior of the eigenvalue. It's asymptotic beautifully. But the Polier conjecture said that actually it's bigger than equal to the estimate. You don't need to be approximate. It's just bigger than equal to. And this Li-Yau estimate is kind of similar to that, I think. So in one side inequality, it is actually sub. You don't need to do WKB method. So this low energy, this low function comes up in the you use a path integration to look at the quantum mechanical system. It appears there, and this low can be is an important quantity, and I think this whole thing could be related to WKB method in quantum many-body problem. I believe people should look into that in more detail.
Thank you very much.
Are there any other questions?
Yeah, I have one. Thank you very much, Dr. Yao, for your presentation and for your explanation of the methods that contributed to the Perelman result and the Ricci flow. I had a question concerning like geometrization, given the continuous result over the surface of a a spherical object. Would that extend as well to, say, a case in which like you had a discrete metric between individual elements, but you could sum over them to form the surface of some like deformed topology?
Well, yeah, I mean, so for 2 dimensions, you can do that easily, but high dimension, you encounter much more problem. And as we know, Ricci flow in the case of surface of genus 1, genus 0, and high genus could be done without any problem. And the convergence is very nice and can be controlled. And so you can discretize those cases. And I think my former student, David Gu, has done, and also with a Chinese mathematician called Law Fan, has looked at the discrete version of the Ricci flow there, and looks like everything goes well. So you can actually use the Ricci flow discrete version of it to understand some geometric computation geometry. We can construct nice, beautiful surface with constant curvature by using rigid flow in a discrete manner. So you can apply it to computer vision. And this was actually a pretty extensive study by them. I think there are books which you can read about that. This was developed about 20 years ago.
Thank you very much for answering my question. Very interesting presentation, sir.
Thank you.